This is called the periodic table. This is a modern periodic table, although it is based on research done by a Russian scientist by the name of Dmitry Mendeleev. We credit Mendeleev with the organization of our periodic table, although there was a German scientist named Meyer who independently came up with a similar grouping of our elements. Now, our periodic table represents what's called periodic law. And that law states that the properties of elements are periodic functions of their atomic numbers. Now, on our periodic table, we have a whole bunch of little rectangles. Each of these rectangles represents an element. In that rectangle, we have, let's see if I can draw a characteristic rectangle here. I'm just going to use carbon. So in that rectangle, we have a number in the upper left-hand corner. That number is the atomic number. The atomic number is the number of protons every atom of that element contains. Then we have a letter or letters, and that letter is a symbol. That's the chemical symbol for that element. Then on this periodic table, it writes out the name of the element, and then there's another number. This number down here, that is called the atomic mass. That is the mass of 1 mole of atoms of that element. So for carbon, 1 mole of carbon is 12.01 grams of carbon. That's what the numbers mean in the rectangles. Now, as you can see on the periodic table, we have columns and we have rows. Now on these, and I'm just going to give these a blue highlight here, we have these elements and they're in this like little stair step arrangement. And that is relevant because to the left of this stair step, that's where we have all of our metals. You see the majority of the periodic table are metals. To the right of this stair step, we have nonmetals. Now, metals tend to be shiny. They're ductile, which means they can be drawn out into thin wires, and they conduct both heat and electricity. Nonmetals tend to be insulators from heat and electricity, and they tend to be dull. The blue atoms, or the blue elements that I have highlighted here, are what are called metalloids. Metalloids are the in-between. They share some properties of metals and some of nonmetals. Now we also have on the periodic table, we have what are called main group elements and we have transition elements. And it might be easier if I just kind of color in the transition elements for now. The transition elements are located here and I'm filling them in just to give you an idea. The remainder are called main group elements. So these yellow ones, those are classically called our transition metals. These rows down here, we call those our inner transition metals. The top row are called lanthanides and the bottom row is called actinides. So with our main group elements here, I'm going to color them each a different color. In this column here, the first column, we call those elements the alkali metals. In the second column, we call these alkaline earth metals, and they're part of our main group elements. So how can you remember alkali versus alkaline earth? Well, see the little 1 above the column and see the little 2? Alkali is 1 word, but alkaline earth is 2. So that's an easy way to remember those two. Then we come over here and we have nonmetals. I'm going to give just a quick fill in here. So these nonmetals are primarily what we look at when we're looking at organic chemistry, but these nonmetals are going to be important moving forward for our class as well. So then we have these here, In column 17 on this periodic table, these are called our halogens. Halogens. You may have heard of a halogen light bulb. It's based on some of these elements. And then lastly over here, I'm going to fill these in. These are called our noble gases. Noble gas, and that's in column number 18. Now, if you have an older periodic table that originated in the United States, it's possible that instead of these numbers, which is the standard IUPAC designation, it's possible that you have Roman numerals and letters. So 1 would be 1A, 2 would be 2A, this would be 3A, 4A, etc. And that continues. Now notice the A designation indicates our main group columns. So this would actually be 1B, and here we have 2B, 3B, etc. So the B designation was for our transition metals. It is possible that you'll never see the A and B designation, and that's okay too. The A and B designation is going out of vogue, and what you may see is just the IUPAC standard, and that's okay too. Now, the oxygen and sulfur, primarily, we can call those our chalcogens, and it's not a common thing. It's not in every textbook, but that is what they are called. So we have these groups, and these groups are organized by some specific chemical properties. Now, if your class has already done quantum mechanics and you've already seen principal energy levels and electron configurations, then you should be able to pick out that all of the valence electrons for column 1 end in S1, for column 2 end in S2, and so on. Now, if you haven't seen this yet in your classroom, consider this a preview. So you will need to know this eventually. Now, this becomes important, especially when we're going to make what are called ions and when we go to make bonds. So if you haven't seen it yet, it's coming up very, very soon. Now, along with these chemical properties, we can see trends as we move across a period and up or down a column. Remember, your periods are your rows, your columns are your groups or families. So one of the chemical properties we have, or physical properties, either or both, one of the properties we have that we can see on the periodic table is the atomic radius. So how large is each one of these atoms? As we move across the period, we are increasing the number of protons. Now, also note we're increasing the mass. So not only are we increasing the protons, we're probably increasing neutrons as well. As we increase that nucleus, it's intuitive for a lot of students to think, well, that means the atomic radius is increasing as we move from left to right. But that's not correct. As we increase the mass of the nucleus, so as we make that nucleus larger and larger and larger, it creates a system that pulls on the electrons more and more. And because, for example, in the second row, we only have the first 2 principal energy levels, as we increase the number of nucleons in the nucleus, that increases the pull on those electrons, and it actually decreases the atomic radius. So as we move from bottom to top on the periodic table, we are removing or we are decreasing our principal energy levels available. And as we do that, we are decreasing the distance away from the nucleus, so we decrease our atomic radius as we go from bottom to top. Now, I've chosen to present this with all of my arrows facing the same way. If you would prefer to write in your notes that you have an increase this way, you go right ahead. Take the notes that make the most sense to you. Now, another property that we have to see a trend on our periodic table is called ionization energy. The ionization energy is the energy required to remove the most loosely bound electron from a gaseous atom in a ground state. If you've done some quantum mechanics and you've seen the electron configurations, then you know that that electron is going to be in the valence shell. So the ionization energy will increase as you move from left to right, and it increases as you move from bottom to top. So since we're increasing the energy required to remove that electron, then these elements in the top right will be less likely to have an electron removed. These elements will be more likely to have an element removed or have an electron removed. So as the ionization energy decreases, the propensity to become a cation or a positively charged ion because an electron is removed increases. The next property we have is called electron affinity. Electron affinity is the energy change of adding an electron to a gaseous atom to form a negative ion. A negative ion is called an anion. So a positive ion is called a cation. So electron affinity is how likely are we to form an anion? Well, it's more favorable as you go up a column or to the right on the periodic table. So if the ionization energy had it more likely to form a cation or lose an electron down here, the electron affinity shows us that it's more likely to grab an electron or make an anion up here. So on the periodic table, what does that mean? On the periodic table, that means these are going to be more likely to be cations. So we're going to put a big old plus. We can hardly see that. A big plus here. And that means that our anions are more likely to form right here. So that will come into play very, very soon. Now, the last property we have is called electronegativity. And electronegativity is how strongly atoms draw electrons towards themselves in a bonding situation. Now, electronegativity is akin to electron affinity, and fluorine is actually the most electronegative atom or the most electronegative element that we have, and the closer you are to fluorine, the more electronegative your element will be.